So I'm going to talk about entanglement in gauge theory, which is maybe something you've heard me talk about before. And actually, Sandeep gave a great introduction to the subject yesterday. What I want to talk about is how our understanding of features of entanglement entropy in gauge theories can lead us to a better understanding of features of entanglement entropy for string theories. And this is work done jointly with Gabriel Wang, who's currently a postdoc at Fudan. Okay, so a little background. A lot of the reason why we think that quantum information tools will be helpful in the study of quantum gravity comes from Ryutake Yanagi, and particularly its generalizations. So in the large N expansion of the CFT, we first have this term, which is the area of a minimal surface, or 4G, the Bekenstein-Hawking entropy. Okay? And still at the classical level, this can be generalized to theories where you have not just Einstein gravity, but higher derivative corrections. It's done by Zhidong and Zhuan Camps. And so that gives the description at the sort of leading classical level, but so far that's purely classical in the bulk. What's maybe even more interesting is that one can go further in the 1/n expansion. And the next thing that one sees is entanglement not of the CFT, but of bulk fields. So, and recently, more recently, it's been understood how to generalize that even higher in the 1/n expansion. So, so this is great. It's telling us that not only do we learn something about entanglement properties of the boundary, we also learn something about entanglement entropy in this bulk theory, which for me is the more interesting thing to understand. But of course, the limitation is that this is all done within a limit or an approximation where the bulk is still just a field theory. It's still just this perturbative thing. And what we'd really like to understand is to go deeper and understand something about the information theoretic structure of the underlying quantum gravity degrees of freedom, or these the stringy degrees of freedom that are supposed to be making up the space-time. I should mention, please feel free to interrupt me at any time. Okay, so what do we expect from entanglement in a string theory? So this question was asked near the dawn of recorded history in '93 by Susskind and Uglum. And they they just did maybe the first thing that you might try to do. They did the replica trick on a plane. So they insert, so here's Euclidean space-time. You insert a conical singularity with angle beta going around. You look at the sum of all closed string diagrams, and that connected ones, that's the log of the partition function. Now, what happens is when you take this particular derivative, any diagram which doesn't interact with this singularity drops out. So if you have just a sphere that's sitting out away from the singularity, that doesn't contribute to the entropy. They have to either make contact with the singularity, or they have to encircle it in some way. They have to wrap around it. What's really interesting about string theory that's not present in field theory is this first diagram, the sphere diagram. That's the object that's responsible for the leading contribution to S, the one that scales like 1/G. So whereas in the field theory approximation, in RT and so on, this thing just gets replaced by some classical expectation value. It's some classical term. Whereas in string theory, one can actually view it as integrating over some degrees of freedom and actually coming from a counting of states. It's actually a quantum entropy. So that was the idea. And if you look at these diagrams sort of going around a slicing that sort of goes around the singularity along this angle, what it looks like, the slicing of these diagrams, they look like open strings with their endpoints confined on the entangling surface. So what this suggested to Susskind is that what you're counting is you're doing something like a trace over some thermal system of open strings ending at the entangling surface, but didn't give a precise canonical description of this sort. Has never actually been worked out. It was just from the pictures, one sort of expects that's how it's going to go. Okay. Yes. Exactly, that's the question. Exactly. So yes, this is a purely Euclidean calculation. And if you try to do this, so part of what makes this interesting is if you try to do this in field theory, these contact diagrams, like the first two, lead to some terms that don't obviously have a statistical interpretation. They aren't obviously related to any counting of states. The first one, in fact, isn't. The second one, in certain cases, you can understand it in terms of a counting of states. So the question is, okay, in this string theory, is this really an honest entropy calculation or not? Okay. So I don't have the technical expertise to carry this out in full string theory. I mean, I think, as far as I know, currently nobody does. But what I can do is I can study a toy model. And the toy model I'm going to talk about is two-dimensional Yang-Mills theory. So it was found by Gross and Taylor in the early 90s that two-dimensional Yang-Mills actually has a string theory dual. So what's nice about this as a model is, first of all, it's exactly solvable, so you can calculate essentially anything you want. One understands the entanglement on the gauge theory side quite well. You can do this at finite n, or understand also the 1 over n expansion of the entropy. As I mentioned, it has this string theory dual, which can be understood. So you have to take the large n limit, but you can understand it at any coupling. So you're really working in the stringy regime. And although this theory has no local degrees of freedom, it's almost a topological theory. For our purposes, that's actually a feature and not a bug. First of all, it allows us to focus on these contact interactions, which are the most important part from the point of view of the gravity theory. They control the leading order piece of the answer, but also we don't need to worry about all the issues that usually plague entanglement entropy, such as UV divergences. And the general question is, how do the features that we understand of gauge theory entanglement entropy turn into the features that we expect of string theory entanglement entropy? Okay, so here's an outline. So our theory is two-dimensional, and the simplest, so in fact, both the Yang-Mills theory and the string theory are two-dimensional. So we're going to focus on the simplest two-dimensional case, which is the two-dimensional de Sitter entropy. So as a Euclidean calculation, it looks like a sphere partition function where we take our entangling surface to be 2 points, which will be these poles here, the north and south pole. Okay. So first, I'm going to talk about this calculation in the context of two-dimensional Yang-Mills theory, just to remind everyone how that works. I'm going to discuss the canonical formulation of the theory, and then the calculation of entanglement. And then I'm going to describe the same calculation, but in the string theory variables. I'm first going to talk about the canonical description in terms of closed strings. But as we expect, in order to understand the entanglement, we also have to talk about open strings. So I'm going to discuss that canonical theory, and finally how one can understand the entanglement calculation in this in terms of open strings as an honest calculation in a Hilbert space with a modular Hamiltonian. Okay. So first, to review two-dimensional Yang-Mills theory. So we're going to take the gauge group UN, and to start, let's consider Yang-Mills on a Euclidean space, which we're going to take to be foliated by circles. So like this cylinder here. We have two canonical variables. We have a Wilson loop that goes around the entire circle. And we have an electric field which takes value in the Lie algebra, it's covariantly constant. So these are our, we're going to think of u as like a position variable and e like a momentum variable that generates rotations of u. No, it isn't. So neither is, so okay, good. So u and e are not gauge invariant. The trace of u is gauge invariant, and traces of powers and so on. Yeah, so good. So that's right. So I'm not, so right now I've got two variables that are both gauge invariant, and I can build gauge invariant things out of them. So the gauge invariant things that I can construct are class functions of u, things that are invariant under this transformation. U goes to g, u g inverse. And I can construct invariants from the electric field, such as trace of e squared, cubed, et cetera, up to trace e to the n. Good. So the Hilbert space that I'm talking about, so u is my position type variable. So I take the functions on the group manifold, but they have to be invariant under this remaining gauge transformation. And then the gauge invariant functions of E act on that space as differential operators. So in particular, the gauge invariant operator that we're most interested in is trace of E squared, and that's just the natural Laplacian on the group manifold. So yeah, right, and the Hamiltonian is just this multiple of it. With involving the 't Hooft coupling g squared n. So it's like, it's essentially quantum mechanics on the group manifold, but it's like you take the sector that's invariant under this transformation. It'd be like doing quantum mechanics, but taking just the S wave or something like that. Okay. So that's our quantum mechanical system. And now, in order to talk about entanglement, we need to talk about the Hilbert space of an interval. Okay, so our canonical variables for an interval, we're going to take a Wilson line, which goes from one end of the interval to the other. And we're going to consider left and right electric fields, which will be the electric fields at the endpoints. Okay. The Hilbert space now is the space of all functions of that Wilson line. We don't impose this sort of gauge invariance condition at the endpoints. And the left and right electric fields generate left and right rotations in the group manifold, respectively. Now, there's another thing that we have to say, which is how the Hilbert space of the circle embeds into two copies of the Hilbert space of the interval. And that's a construction that I think both Sandeep and Daniel talked about yesterday. What one can do is, of course, right. So of course, this Hilbert space doesn't split as a tensor product, but there's a natural way to embed this space into the larger space. And the way you do it is that there are these leftover gauge transformations at the ends. So when you fuse the two Hilbert spaces together, you have to mod out by those. So that's implemented as this quotient here. And we called that the entangling product, just to give it a name. Okay. And essentially what that's doing, that quotient, is it's identifying the generators of these transformations. And what that's saying is that the electric field has to be continuous across that cut. But one can embed this Hilbert space into the ordinary complex tensor product and calculate entanglement entropy as usual. So there's a simple way to do that. It turns out to be easiest in a particular basis, the so-called representation basis, whose wave functions are characters of irreducible representations of the group. So we have a particular orthonormal basis in which we can expand any state. And what's nice about this basis is that it tells you exactly how it transforms under these residual gauge transformations at the endpoints. And so just from knowing the probability distribution in this, so in fact, you don't even need to know the phases of this state in that basis. Just from knowing the probabilities of your state, one can find the entanglement entropy. And it's given by this formula that I think Sandeep showed us yesterday. The difference is he had one extra term, which had to do with this sort of bulk entanglement of the theory, this sort of quantum piece. And that's absent here just because the model has no degrees of freedom. And the number 2 here, multiplying the log of the dimension, just comes from the 2 points that make up the entangling surface. So this is a non-abelian generalization of what Cassini, Huerta, and Rosabal called the electric center choice. In two-dimensional Yang-Mills, it's really the only, at least in this model, it's the only choice. There's no magnetic field. So now we can look at the example that I wanted to, which is the de Sitter entropy. So, which is just the entanglement entropy of the Hartle-Hawking state. So we prepare the Hartle-Hawking state by doing this path integral over the hemisphere. And because this theory is so simple, one can work it out explicitly. So there it is. It has this e to the minus lambda a. So this was the Hamiltonian of the theory. C2 is just the eigenvalue. C2 of the representation is just the eigenvalue of the Hamiltonian. So this is the sort of thermal weight that one would expect. And one has this dimension of R factor, which comes essentially from inserting a tiny disk at the bottom of this sphere. And that tells us the probabilities and the entropy as follows, and the entropy just follows precisely from the formula that I gave on the previous slide. And it gives an answer that agrees with the replica trick just applied to the sphere partition function of the theory. So what it's showing is that this, something that was mentioned yesterday, it's shown one can see quite explicitly that this extended Hilbert space construction matches up with the replica trick. This 1 minus a d by dA just comes from the fact that the area, the partition function is not sensitive to the conical angle, it's only sensitive to the total area. So in doing the beta variation, so one can replace the beta variation with an area variation. So just as a side note, often, so there's been some discussion, in particular, I think I came to an understanding of this sort of thing through discussions with Horacio over email. Why do we need these so the question always comes up, why do we need these extra things? It looks like there's some extra some things that you just put into the theory by hand in order to split the Hilbert space. And they're not really, they shouldn't really be there. But actually they have an important consequence. So in fact, so what they do is they're necessary in order for the theory to have a modular Hamiltonian that's represented geometrically as the de Sitter boost in this case. So to see that, one can consider some local observable. So for example, trace of the electric field. And one can calculate it 2 ways, either just from the Hartle-Hawking wave function. So that's the first line here. Or one can use the modular Hamiltonian in the static patch. And that's the second calculation where I've used the fact that we know what the energy levels, we know what the Hamiltonian is as a function of the electric field. It's just the trace of E squared. But we may not have decided what the degeneracy of each level is. But then clearly, in order for these 2 calculations to match, the degeneracy of this level has to be the dimension of the representation squared. In other words, these extra gauge indices that live at the end of the interval are important not only to match up with the replica trick, but to reproduce expectation values of physical observables. And in fact, we'll see they're essential in order to have the correct large N scaling of the entropy. What they do is these extra degeneracies say that the thermal partition function is going to favor larger representations than it would if these factors weren't there. There's this extra weight, And so it drives the entropy up. Okay. So that's the Yang-Mills theory, and now I'm going to do the same thing, but in terms of the string theory description of this model. Good. So Gross and Taylor gave us the rules for how to calculate the partition function of this theory in a large N expansion as a sum of branched covers of the manifold. So both the world sheet and the target are two-dimensional. The world sheets can't fold back on themselves, so the only thing that they can do is they can just wrap the target space. And they're allowed to have these these branch point singularities where you can go around them and wind up on a different sheet. Okay. So we sum over possible world sheets sigma and maps nu from those into the manifold. There'll be n-fold covers with I branch points. And then we integrate over the locations of the branch points, just like you would integrate over the location of interactions as usual. We have a power of the string coupling. That's the Euler characteristic of the world sheet, which tells us that the string coupling is 1 over n. We divide by a symmetry factor, as usual, and we weight by the exponential of the Nambu-Goto action. And that also allows us to read off the string tension, which is given by lambda over 2. And this gives us our partition function as a power series in 1 over n, in lambda a, and in e to the minus lambda a. So it's including effects that are non-perturbative in the strong coupling expansion, but not in the 1 over n expansion. The canonical version of this theory, if you think about slicing one of these diagrams at a single time along a circle, then the world sheets are going to wind around some number. The strings are going to wind around the spatial circle some number of times. We can describe some set of strings just by a permutation. So we take the strings around, and then at some point we act with a permutation, and they keep on going, so that each cycle of the permutation represents a winding number of one of these strings. Our Hamiltonian has 2 terms. The first one is proportional to n, the number of strings, and their length. And the tension, this is just the Nambu-Goto energy of a string, tension times length. And the second is an interaction, and what it does is it takes two strings at a point, cuts them apart, twists one, and glues them back together. And that's the second term. It has an interaction strength given by the coupling constant, 1 over n. And it changes the winding numbers of the strings by this cutting, like in this bottom right corner. There's another sector. The strings are oriented, so they can wind both ways, but the two orientations don't talk to each other. So it's just 2 copies of this theory on a cylinder. Okay. But when you study the theory on the sphere, something funny happens, which is you have to include these some additional singularities into your partition function. In particular, you have to fix 2 special points on your manifold, which are called omega points, or Gross and Taylor called them omega points. And there you allow for an arbitrary permutation of the sheets as you go around the point. So as you encircle the omega point, there's no sort of smoothness imposed there. You could come back arbitrarily, the sheets can come back arbitrarily permuted. Moreover, at these omega points, the world sheets with different orientations can interact. So you can have two sheets of opposite orientations collapsing into this point. And there were certain rules associated with these points. Okay. For each non-trivial permutation, such as depicted on the left, you get an n to the number of cycles. So there'd be an n squared associated with that state. And for every orientation reversing tube, this thing on the right, you get a factor of -1. And the omega points, unlike the other interactions, aren't integrated over. You just stick them somewhere. These things are kind of unusual. They were just found, but basically by a brute force evaluation of the Yang-Mills partition function. They just ground out the combinatorics. It's impressive, but in the end of the day, you get this thing. And who ordered that? Okay. Yeah. Oh, thanks. Okay. Okay, so there are, so now we have to go, in order to describe entanglement, we have to go from the closed string slicing to an open string, to this open slicing of the sphere. So whereas in the closed string channel, the sphere partition function looks like an amplitude between these two funny omega states, we want to describe it instead as this evolution of an interval in terms of the interval Hilbert space. Okay, so the Hilbert space of an interval is described by open strings. So we'll have some collection of strings which have Chen-Payton indices on their ends, which run from 1 up to n. Our electric fields will permute these indices. And again, there's an entangling product that tells you, that is the same as the Yang-Mills one. It tells you how to take some closed string configuration and cut it into two open string configurations. It tells you that the indices have to be related by this permutation that defined your closed string. Okay. So that's our string theory version of the entangling product. Now there's one additional subtlety for open strings, which is that, again, there are two sectors. The strings can go both ways. But now the two sectors talk to each other. Within each sector, the Hamiltonian is exactly as before. There's a Nambu-Goto tension type of term and an interaction that twists the strings together. But the two orientations don't decouple. In fact, the states aren't independent from each other. There's the equation U dagger equals identity and U dagger U equals identity tell you that there's certain states with n strings going one way and n bar going the other way is equivalent to certain states with n minus 1 and n bar minus 1 strings. So the two sectors aren't independent. And from these rules, from the fact that the two orientations aren't independent, and the fact that we have these Chen-Payton factors that we have to sum over, give precisely the rules for the omega point. So this thing that appeared in the path integral is really rather naturally explained from the open string point of view. This factor of n to the number of cycles that appeared whenever you had a permutation going around the omega point, that's giving us the sum over the Chen-Payton indices. And the factors of -1 associated to the orientation reversing tubes, we're correcting for this overcounting of states. The fact that there were states which looked like, which had different string descriptions which were secretly the same state. And once we have this, we can write our sphere partition function as a trace. And one can check that that it gives the same answer as this Gross-Taylor path integral, but now it's expressed as a trace over this open string Hilbert space in terms of, which I described before, and this open string Hamiltonian, which implements the time evolution with interactions. So what we see is that this omega point we should think of as a sort of brain that sits at the entangling surface. We called it an entanglement brain, or maybe to be slightly tongue-in-cheek, an E-brain. And we see that, to sort of summarize, the entanglement entropy is counting open strings, which are stretching between these E-brains. Okay, so just to sum up, we found that the entanglement entropy in two-dimensional Yang-Mills at large n is just precisely equal to the entanglement entropy of its dual string theory. There's the fact that in gauge theory, you have to add these sort of charged-like objects at the endpoints of the interval in order to split the Hilbert space is reflected by this entangling product where you cut where you have to cut a closed string into open strings. The entanglement calculation requires the insertion of these entanglement branes, but maybe what's surprising is that we didn't really have to put them in. In some sense, they're already there in the theory. The Euclidean partition function already knows about these states. And the n-squared scaling of the entanglement can be directly traced to the fact that you have to sum over these Chan-Paton indices of these open strings. And I think what this suggests at a broader level is that if you have a duality like this, where you have a duality between gauge fields and strings, if you can really treat the string side as a string theory, not in its field theory approximation, then one can actually recover the entire entropy. So to put it as a slogan, boundary entanglement equals bulk entanglement. That's true in this simple model. What the right-hand side of this means in the real context, say, of type 2B string theory, I don't know. Okay, and there are a bunch of areas of future work, but I think since I'm out of time, I'll just stop there. Thank you very much.
A little bit of time for quick questions. Yeah.
So if you take a lattice gauge theory and do the strong coupling expansion, you can recast it in terms of sum over discrete surfaces, very
Yes.
complicated rules. So you think there is a generalization to of this
Yeah,
idea there?
yeah, I've looked at that. I've looked at that a bit, and certainly you can do that, and you get again you get this. In a sense, you can see a lot of these features. I mean, the lattice is really just many copies of this theory glued together at vertices, right? So in some sense, it's the same story. The tricky thing is to get from that strong coupling expansion into the continuum limit. So you can do a sort of perturbative strong coupling expansion, this sort of Kogut-Susskind approach, which I did a little bit in the finite end theory. You can start writing down terms in that expansion. George Radicevich went a little further in that he did it in the large N theory, but the problem is you're sort of stuck in this strong coupling lattice phase, and you don't actually get to you're never going to hit a field theory. So I don't know. I think it's an interesting approach. I just haven't been able to get to the continuum. It's a hard problem.
This entanglement brain is an object of the theory, or is just artificial? I mean, it's an excitation of the theory, or?
It's still a little bit it's still a little bit mysterious to me. I mean, it exists so we didn't put it in. It exists there in the theory. But it isn't an excitation in the sense that you don't integrate it over it. It's sort of like if you like, it's almost like part of the classical background that has to source the geometry of the sphere. That you sort of couldn't have the number of omega points that you put in is related to the topology. There's just that's the general rule. So it's equal to the Euler characteristic, which is why you have two of them on the sphere. So yes, they're objects in the theory. They're not dynamical in the sense that you don't integrate over them. They're just things that are there. Yeah, exactly what that means for the higher dimensional case is still a bit maybe still a bit puzzling to me. I don't know of anything that acts like them in the higher dimensional string theory, and yet in this particular story, they played an important role in being able to write the theory as an open string theory.
one final question.
You can explain this to me later. But the argument you referred to about the log dA term actually being needed for De Sitter boost invariance went by kind of quickly.
Oh, sorry. Yeah. Well, okay. Since I have to do it quickly again, maybe that won't be maybe that won't be helpful. But yeah. But maybe maybe I could just sort of explain it in terms of a bigger picture. You might ask, why is the entropy? How do you measure entropy, right? So, in order to distinguish which of these is the correct definition. So, like an information theorist might say, how many Bell pairs can I extract? Well, as you showed, in this case, you can't extract any. So that's not the right question. But if you think thermodynamically, which is essentially where this comes from, you want to say this entanglement entropy is actually just a thermal entropy. So thermodynamically, what you can do is you can say, well, what's the I have two levels with different energy. What's the relative population of those two levels, right? It's related to the Boltzmann factor. It's related and the degeneracy of the levels. And so just from being able to measure some observable that tells you the population of each of these levels, you can read off what their energy is, and you can read off what their degeneracy is. And then once you have that, you know what the entropy has to be.
Okay, I think it's time to end.
Great.
Let's thank
Thank you.
Bill again.